I would like to make this presentation about recent trends and developments that I think are really interesting in machine learning and happening these days, and that are likely to have an impact in the short-term future. I have quite a lot of content. I'll try to squeeze it in 45 minutes and leave some room for questions. But if we are a bit tight, I'm also happy to take discussions offline afterwards if you want. Okay, just a few words about me. I'm an EPFL product. I was trained at EPFL, did a PhD in computer science. Then I spent a few years at Swisscom working on big data and in the mobility insights team, where we had this really interesting projects about quantifying the mobility in Switzerland using network data. And for about 3 years now, I work at Unitate, and I'm leading different deployments and also some machine learning initiatives that we have at Unitate. So just one slide on Unitate, just for you to know a little bit who we are. So we are a relatively fresh company because we have been established in 2017. But we're growing quite fast. We are already about 60 people, and we have offices in Zurich, in Lausanne, and also in Krakow, in Poland. And our mission is really to help traditional industries that are not digital natives with top-level data science capabilities and skills. And for that, we do everything from consulting on use cases, technical consulting, but also engineering work, data science, machine learning, etc. So end to end. So I want to start the presentation with a few words on AI, because machine learning is very often linked with AI these days, and is probably what comes the closest to implementing AI. And I want to say a few words because I think the AI dialogue today is sometimes a little bit difficult because we hear lots of voices and we hear lots of opinions. So I just want to try to give a very high summary of those. So, we have people like Elon Musk saying, okay, AI is super dangerous. It's more dangerous than nuclear weapons. We are summoning the demon. The day will come, we'll build an AI so smart, we won't be able to control it. And in front, we have people like Steven Pinker saying, no, I mean, if we are, so smart as to create a really good AI, will be smart enough to control its goals, right? But we also have other people that are writing books about topics like singularity and sort of proving on paper that this will happen, it's unavoidable, and will all be turned into paper clips. For example, if the AI decides to optimize the paper clip production, right? We also have people like Rodney Brooks, who is saying, anyway, this is all inflated hype. What's happening today is really not special, but also at the same time, sometimes making really precise and weird predictions about the future. And we have also sometimes journalists or other people using terms that are sometimes a little bit not precise and might be also a little bit scary, like exponential technology, which I'm not exactly sure what it means. And in the middle, we have folks like Jürgen Schmidhuber, who is, often right, but he's saying, oh, look, this is also, this is not you. It was all invented in my lab in the 90s. So, let's not be so excited. And we have also folks like Benjo saying, maybe AI or general intelligence is coming, but we have more pressing social issues related to machine learning today. So, things related to, for instance, AI taking jobs, but other people are replying, no, actually, it won't take jobs. It will produce more jobs because that's, just what technological revolutions do. And then we also have all these worries about trying to make our algorithms less stupid. So for example, less racist and sexist than the data sets they are trained on, which are all like super important concern, at least in the short term. And then there is politics also in the mix. So there is US versus Europe versus China, and some are now saying that China is on track to become leader there. And in the middle of that, we have some, let's say, skeptical practitioners who are thinking, yeah, anyway, this deep learning business, I'm not sure, because I can do 99.9% of what I need using only linear regression. So, this is also all hyped up. And I relate a little bit to that, but I'm a bit more optimistic and enthusiastic. But it's true that tech practitioners, sometimes we feel a little bit like, like this picture describes. So we hear lots of philosophical conversations about AI destroying the world, but in practice, we're still sometimes struggling making, models do silly things. But still, I think all these philosophical discussions, they're really good. They're really important. I mean, important things are happening these days. And they are good to have. But now for this presentation, I just want to be a little bit, let's say, more down to earth and look really at what's happening today, what has happened over the last 2-3 years, and what is very likely to have concrete impact in practice for, in the industry. So I want to start right ahead and starting to dive deep in the topic, and here I want to give a small disclaimer. I have been asked to make this talk at least partly technical, so I apologize in advance for non-technical folks among you who perhaps are not too much into that. This what comes will be my most technical slide, I think. But I promise it gets better after that, and you can just relax and enjoy. Even if you don't really understand, it's okay. You will get the rest of the presentation. So I want to talk about this attention mechanism, which is one of the key Lego blocks that we're seeing, which are changing many things in machine learning since recently. So machine learning today, it's all about deep learning, and deep learning are neural networks, and neural networks are just layers stacked on top of each other, right? And if we look at what we used to have traditionally, the canonical layer was this fully connected layer here, where you have some input vector x, and you do some linear mapping, and you obtain a new output vector x prime, and the linear mapping is what you learned, and it's fixed. You learn it on data, but once you learn it, it's fixed. This works well in many cases. We have better architectures, like for images, we use convolutional networks and so on. On sequences, so when the x doesn't have a fixed size, we can use recurrent neural networks, where here, we try to store some memory of what we have observed in the course of the sequence. So here, the sequence is the x, but it can vary over time. It can have arbitrary length. And here we memorize what matters in the sequence, and then the model basically uses this memory to make its outputs. This is also very good. It can work on sequences, but it's challenging because it's challenging for these networks to memorize what happens in the course of the sequences when the sequences are long. So imagine a long piece of text here. It's hard for the networks to remember what happened at the beginning. And now what we're seeing is attention, which is really sort of eating a little bit the machine learning architectures these days. So those are new types of layers, which take sets of vectors in input and output different sets of vectors. And now the difference with fully connected is that we still have, each input can be potentially connected to each output, but the connections happen dynamically based on the data, based on the input, right? So here, what we'll have is that each output node, for example, here the third node, will compute a weighted average of the values that it receives in input from each of the input nodes. So these values are also vectors. And the coefficients here, the sort of attention weights, they depend on a sort of measure of compatibility of, what, for example, node 4 has to offer and how compatible is it with what node 3 is interested in, This is a fairly abstract notion, but it's very powerful. So basically, this is the way these weights are computed. They take the dot product between these queries and keys vectors, which allow basically these output nodes to index and select what they will be looking at, what they will care about in the inputs, right? So for example, here, the third node perhaps cares a lot about what the second node has to offer, a little bit about the fourth node, and not too much about the other two, right? And this is dynamic. It depends on the data. So there is a sort of dynamic routing going on, which is really powerful. And basically here, this is a set of vectors, but we can also make it work on sequences if we encode the position of the vectors, in their dimensions, basically. And here, the output, doesn't have this memory problem that we had for recurrent neural networks, because here the third node, for example, can just look at any other node, and it doesn't depend on the distance in the sequence. So we don't have this memory problem anymore. It's replaced by some other computations, scalability challenges, but it's not there anymore. And also, this dynamic connections idea is really sort of implementing an indexing mechanism. So node 3 can really index and select which of the inputs it's looking at, which is really general. And like I said, more general than the fully connected layers. So the fact that it's more general is actually very interesting because it means it's more powerful, but it also means it has to be trained on more data, which is also perhaps part of the reason why it's coming around these days, because we have lots of data. So what happened for natural language processing is a paper that all practitioners in the field know very well. This paper was called "Attention is All You Need," published in 2017. They introduced this transformer architecture, which is really a systematic use of these attention layers plus other things around. But basically the key building block here is using these attention layers a bit everywhere. And it's a state of the art ever since. So all the new natural language processing models that you see out there now, they are based on that. So BERT, Roberta, also these new GPTs from OpenAI. I will talk about them in coming slides. And this architecture is really good because we can use self-supervised learning on it. Basically, we can just take any piece of text or basically scrape the whole internet. We don't need labels. We can just train the models on the text directly without labels. There are great ways to do transfer learning using that. So that means you don't have to train from scratch your own models. You can just use models trained already by someone else. And for example, using these libraries like Hugging Face, which is really good. And these architectures, for the moment, this is really it. They replaced LSTMs. LSTMs for NLP is basically gone, right? Which is something, in 2017 that probably would have been quite hard to conceive, I think. Just for those of you who might be interested, this is what the actual architecture of the transformer looks like. So without going into details, it's stacking many of these attention layers. So the orange boxes here are these attention layers, and the rest are just more classic neural network layers that are being used. So these latest models by OpenAI, GPT-2, GPT-3, they are really simple. They are huge, but they are very simple in the way they work. So basically, these models, they are just trained to predict the next word always, right? So you give it an input, which is a sequence of words, like language models predict the, and then the model just is trained to predict the next word, right? So here that would be next. And then you can do this over and over. So you can take the output, use it, as an input, append it to your sequence, and again ask the model to predict the next word. And then doing this repeatedly, this is called auto-regression. And when you do this repeatedly, you can use it to generate text. So these models can just be used to generate text, which turns out to be very useful and give them very generic capabilities. And also this simple way of training, like I said before, means you can just take everything you find on the internet, every text, and train these models on them. They just need to try to predict the next word every time. So this is really simple. What GPT-3 is bringing is this basically implementation of zero and one-shot learning, which I think this is really the big deal probably behind GPT-3. So I'll try to explain how it works. Basically before 2020, the old way would be what we call fine-tuning. So basically, if what you're interested in is to translate from English to French, you would take a pre-trained model, a model trained by someone else, but you would still fine-tune it. So you would still show to this model some examples of translations from English to French, do some gradient updates, so fine-tune the weights of the models, show more examples, do some gradient updates, etc., etc. This is good, works well, but requires a data set per task. Here you need a data set with examples that are labeled examples between going from English to French. The new way with GPT-3 is really that simple in a way. So the whole idea is that if the model is big enough, if it has seen enough text, you can maybe just give as input to the model some text, and in the text you give in input, you just describe the tasks that you want to do, right? So as input, you can give to the model translate English to French, cheese equals. And then by just predicting the next word, if your model really is smart enough, it should, output fromage in this case. One-shot learning is similar. You describe the task, and then you just give one example. Just one example, one labeled example if you want. So sea otter is loutre de mer, then cheese is, and then the model, so you hope that it's smart enough to figure out from the example, oh, okay, that's the format you're using after this character. I have to give the translation. So, there you go, cheese is fromage, right? And it's pretty amazing that it works in many tasks. So for GPT-3, they managed to reach state-of-the-art levels using this zero and one shot or few shots learning. So for example, here I'm showing a plot, showing the accuracy of some task, some NLP task, which is on question answering. And you can see that on the really, really large versions of GPT, the biggest one, using one-shot learning reaches the state of the art. So that means it reaches the level that was obtained by the models, the best deep learning models before that, the ones that were really trained on this task. So that's really cool, I think. That's really powerful. And here, yeah, also, sometimes people have opinions about the results of these models and the quality of the outputs and what it means, etc. But I think, irrespective of your opinion, I think it's quite impressive to see what this model generates. So, it's able to generate text that is looking like decent text. Sometimes people have a hard time distinguishing, if this was written by a human or by a model. But it can also do simple arithmetic, which is also quite impressive because this model has never been trained to do arithmetic. It has just been trained to predict the next word. But it has seen so much text that if you prompt the model with a text saying, question what is 34 minus 53, answer column, the model would output minus 19. In this case, it would be correct. It's not always correct, but it's often correct, which is quite impressive. It can also do code generation. So Here is a funny example. I'm not sure how really well it works, but I think they make it work on toy examples. So you could describe an app, like add, a button that says this, another button that says that, and then, I click here and this should happen. And the model is actually generating code because it has also been trained on code that it found on the internet. So it sort of learned to code in a way. So one very clear trend with these models, because they are based on this attention mechanism, and this is such a general architecture. It requires lots and lots of data. And there is a trend these days that all the newer, better models tend to be bigger than the ones before. So you can see here the number of parameters of these models starting in 2018 until one recent one that I found from January 2021, which goes all the way to 1 trillion parameters. And these models, as a consequence, they are, it's not a small task. It's not something you can just train on your laptop or even on a cloud instance that you use, right? It's something that is very substantial, requires a lot of engineering work also to train them, and is very expensive. So, for example, GPT-3 is some figure between $4 and $5 million if you just want to train it, right? Not, oh, sorry. Okay, let me just, I don't know what I did, hit the wrong button. Okay, sorry for that. So this is really substantial. So this means it's not really for you and me to train these models anymore, right? Then there is this very interesting study showing how the quality of the models increase when you increase the computing power that you have, the data set size, or the number of parameters. And every time there is a clear trend, at least in the current regimes, where if you want just like to increase your model quality by 1 unit, let's say going from 5 to 4, and 4 is better here. You have to multiply the computing power that you have at disposal by some factor, for example, about maybe 100, something like this, right? So here, this is pretty clear that the requirements of these models are exponential. So you need exponentially more compute power, exponentially more data, and exponentially more parameters to obtain sort of a linear improvement in your loss, in the model quality. So when I hear these terms like exponential technology, I'm always not really, I'm sometimes a bit confused by exactly what that means, because what we can see from these results is that actually we really have exponential requirements. So probably the technology here, maybe it should be called like logarithmic technology and not exponential, because it's actually, yeah, I find it a bit confusing. So what are consequences of these large text models? So obviously it can be used to write, fairly simple pieces of text that I think that can have some value already. But I think something really cool that I would like to try if I had access to the GPT-3 API would be, recommendations, for example. So assume that I am a certain person, and someone public enough, hopefully, so that my tastes are captured on all the text in the internet. And my favorite book, for example, on a certain topic is, and then you let the model do recommendations. Might perhaps also be used someday for generating code snippets. I don't know about that. Maybe we'll see. Doing other boring stuff like parsing invoices, which I think is a silly challenge that still isn't really solved. Other big consequences of that is that these models are becoming so large that they will just be trained by a handful of large players like Microsoft, Google, OpenAI, and so on. And we'll all be using them through APIs. So that will change the way to do NLP. We'll stop, we won't be the ones training the models anymore, I think, at least for NLP. will be API users, basically. So that raises lots of new questions. Among these questions, we have, the fact that it might become easier to access these models because it's just about calling an API. But it opens the question of who controls the gates. Is there some filtering on the content? Who controls really the models, like the training, the training data, maybe the bias it contains? That becomes more risky if only a few actors can do it, right? And some people are questioning maybe GPT-3 is, not that smart. It's just a very good fuzzy indexing scheme of the whole internet, which is phrased like that, in my opinion, already super nice. But perhaps it doesn't really matter. So, we can question whether it does reasoning or not. Maybe reasoning is a form of being able to really retrieve the relevant sort of data set or piece of data in a given context. I want to talk a little bit about attention on graphs. So depart from NLP and talk about another domain and see how it can be used for solving combinatorial problems. So these attention layers, they can also very sort of naturally be applied on graphs. So the way it would work, right, is you simply would deactivate the sort of connection between an input node and an output node in the layer if these two nodes are not connected in the graph that you're looking at. So for example, here between node 4 and 3, we set the activation to 0 because node 4 and 3, they are not connected in the graph, right? It's as simple as that. And in this case, we can see attention as a sort of message passing algorithm going on in the graph, but which we can learn using backpropagation. So one way to see these vectors here of corresponding to each of the nodes would be to see that as node embeddings from the graph. And once we have these nodes embeddings, we can also obtain graph embeddings, and we can do many things. So one very interesting, I think, application of that sort of canonical application maybe is to try to apply it on the traveling salesman problem. So this problem is very, very famous in computer science. It's about trying to find a loop that is connecting n vertices in a graph and returning to the origin. And we know it's a combinatorial problem. It's very hard. It has been studied a lot, but it's also it's also a very important problem. So not just for routing, I don't know, Uber drivers, but also for doing things like DNA sequencing or chip manufacturing. And here the state of the art that we have today. So today for traveling salesman, we have very good solvers that are actually really, really impressive. So they are able to find, optimal solutions for problems that are already really large. So for example, here finding, the longest pub crawl across the UK. I think this is a very important application of the traveling salesman problem. But it takes a very long time. It takes, in this case, this took like 300 CPU days to find the solution. So, it's solved and not solved at the same time because it takes very long. So here there is a paper that came out in 2018, which is using attention on graphs to try to learn this routing. So basically using these node embeddings and the graph embeddings, the algorithm is trained using reinforcement learning to always predict which should be the next node to visit, right? Assume you're the traveling salesman. The network in a forward pass, it just tells you this is the next node you should visit, right? And you can see, so the results they get, this is the last row here. They have some optimality gap, right? So that means the network is not finding optimal solutions, but it's not very far. It's finding good solutions. The interesting thing is that it's finding these good solutions very fast. So if you compare here to Concord, which is the best solver these days, on 10,000 instances, it took 2 minutes to find the solutions, whereas with the neural net, it takes 2 seconds, right? So I think this is also very, very interesting. And As consequences of that, yeah, I think, so first the consequence is, that's an example of attention, being applied to other domains. So it can be applied on graphs, but it can be also applied on computer vision and other things. So it's really sort of eating a little bit this architecture landscape. And I think the fact that we can now use it to find approximate solutions very quick to tough combinatorial optimization problems, this is really nice because it opens the door to new use cases, things like real-time optimization. So if you are the traveling salesman, you don't have to compute once in advance your route, and with an expensive optimization, you can just do it continuously and also adapt, to time varying conditions, traffic, and you name it. It's very promising because this traveling salesman problem is an NP hard problem. So if we can find decent approximations to it, that's also a very good hope for other tough combinatorial problems, I think. And here it's using reinforcement learning as well, which basically also can be used with pretty much everything that can be simulated. So here in the simulation of the traveling salesman, it's not really simulation, but basically they can just evaluate how good the solution is, right? They don't need to actually carry expensive experiments. Another topic that I really like is the one of data-driven optimization and using generative models. So let me explain here what this means. So before, in classic sense of the term, optimization, so mathematical optimization refers to, trying to minimize a certain function f. So, finding the x such that the output of this function is minimized, such that this x belongs to some domain, right? And usually we have some closed form expressions for these functions and these domains, and we can do things like sometimes convex optimization if it's convex and so on. But imagine now that we have good models. Imagine that we have a good model which is predicting certain things about x, like certain properties of this x, right? This model is also a function. It's a function, and we can try to find the x that is optimizing the output of this function, right? So in this case, the function would be defined by the neural network. The parameters of the functions theta here would be learned from the data. And we would want to find some x that is still in the sort of data manifold, which doesn't have a closed form. So this is let's say, the machine learning version of this optimization problem. So to give a very concrete example, imagine we want to create sort of the ultimate car. So we have this car engineering challenge, and imagine we have a good model that is predicting how good our car will be, given the shape, given the engine, given the transmission, what will be the CO2 emissions, how fast will it go, and what will be, like, how well will it sell, for example, right? Imagine we have this model, it's trained, it works well, it's a predictive model. Now, I think very often what we're interested in would be, okay, good, I have this, but what I really want is to find the shape, the engine, and the transmissions that I should put in my car so that I minimize the CO2, I, perhaps maximize the speed, and also maximize the return on investment, right? Something like this. This is a very hard to define problems in closed form, and the only hope is to tackle it if we have a good model like that. And really, very often, this is what we're interested in. Very often in machine learning, actually, predicting is nice, but the end game often is really in optimizing, trying to find the best possible things to optimize. So here, a sort of naive first approach could be to use an optimization algorithm and try to optimize the inputs the way we would optimize the parameters of the network. So, we could do that using gradient descent. I won't go into the details. But basically, this doesn't really work. Okay, so we tried this on, to give an example, we tried this approach on NIST, and we tried to ask, to optimize a 7, so an image of a 7, and trying to make it look more like a 2, right? And what you can see is that over time, over the optimization taking place, our model becomes more and more confident that this is a 2. But actually, if you look really at the image, it's not a 2, it's just like a 7 that is becoming a bit more blurry, maybe. And this is because really what we're doing is creating an adversarial example. So what we're doing is here, when we do this optimization, we are going outside of the data manifold. We are finding an image that doesn't really make sense, but that is very good at tricking the model into thinking that that's a 2, right? So here there is a very promising approach, which is doing this optimization, but in sort of the latent space. So if we learn the latent space of the NIST digits, we can obtain something like this, you know, where each color represents a digit here. And we can do that using variational autoencoders. So if we take the NIST example, we can learn a smooth latent space like this in the sort of bottleneck layer. And then from this latent space, we can predict, you know, what digit it is, but also, for example, how thick it is. And once we have that, we can try again our optimization in the latent space. So once we do that, we can try to make, for example, digits thicker, or digits, you know, more like a 2, for example, or more like a 0, or whatever. And it works. So it works because in this latent space, you know, it's basically smooth enough, and it has certain properties which make it more less likely to go out and generate garbage, right? So I think this is also really, really cool, because here in this case, we just made this experiment, you know, it's really nothing very complex. The model has just been trained to recognize digits, but by recognizing digits, it can also optimize them and generate, you know, generate different digits. When you apply these to other problems, you know, not toy problems like generating images, but things that are really serious, like optimizing molecules, you can do the same sort of things and try to create new molecules that are more likely to be good drugs, right? I think this is one of the most promising applications of machine learning these days. So this optimization in latent spaces. And this is data-driven because there is no way that we, by hand, capture the equations of what is a good molecule. This has to be learned on data sets of molecules that we already have. This is linked to generative modeling, and you know, there was lots of progress on that in the recent years. So all these faces that you see here, they are faces of people that don't exist. So you know, generated by GANs or by also VAE. Since recently, VAEs also start to have really good generative capabilities. So imagine using these. We are really good now with images. Imagine what will happen when these generative models are also starting to be applied to other domains, not just images, but things like molecules. Right? This is really, really, really nice, I think. There are some funny examples. I have to go fast, or don't want to go too much in details, but basically using GANs, you can sort of reverse engineers the latent dimensions and you know, get synthetic samples that have certain properties that you like. So this stuff, like I said, this is really promising, and it can be used for, I think, very high potential applications. So things like drug design that I mentioned, which is maybe the first one that comes to mind, but also engineering. So I gave this toy example of car design. This is a little bit silly maybe, but imagine being able to design pieces of a car and optimizing the aerodynamics of it if you just have a machine learning model to capture these sort of things. Can be used for chemistry, in other domains, experimental sciences, so how to come up with the best experiments possible. Maybe arts also, although perhaps it's a bit sad to see arts as a form of optimization, but I think it's also interesting maybe to explore, and other domains also that will come, I think, in the coming years. Yeah, I have to go quickly on this one. I'm already a little bit late, but I just want to show examples of recent work that are basically using semi-supervised learning to get really good performance on classification tasks using only 250 labels, right? So I think this is a very nice, I put the reference to the paper here. It's a very nice paper showing how, with just very little labels, lots of data, but only few labels, you can build classifiers that are quite competitive. Recently, OpenAI released a new model, which is called CLIP. And this new model, it's basically this is only one model trained only once. And you can use it on any image data set like ImageNet or others like, food data set or others. And it sort of works pretty well out of the box. So this model has been trained to match text and images, and it can tell how well a text match an image. So it doesn't have to know the labels of the task in advance. It can just figure out the match independently of the task. So this is also very powerful. This is really recent. I think it's gonna I think it's quite equivalent to something like maybe, in a sense, perhaps BERT or GPT-3, but for computer vision, because it's just a generic classifier. So if you have CLIP, you don't need to train your own image classifier. This is over, right? I don't really have time to show exactly how it works, but basically it's trained to map text and images in the same latent space and making the representation of text close to the representation of the image that it matches, and then using that to compute how well a certain text matches a certain image. It's also subject to some silly attacks. So, for example, it's basically recognizing text in images. So, if you put, if you just write iPod on an Apple, it will classify it as iPod. I don't think that's a deep flaw, but it raises new questions about the security of these models, for example. Yeah, here also I will go very quickly over this one, but basically this model, they discovered that because they mix text and image, it actually became really, really good at learning higher level concepts. So for example, they discovered it has a neuron for certain emotions like shocked, or a neuron for Christmas, right? Which is one of the holy grail, for a long time was one of the holy grails really of machine learning, is to learn these higher level concepts. And we can do that much better when we are mixing text and images. So yeah, this is sort of the take-home message I want to bring here, is that we can now do machine learning on much fewer labels. We already saw zero-shot learning for GPT-3, but this sort of stuff is also coming to images, right? And this is way closer to the way humans are learning, because if you show a kid a photo or a picture of an elephant, it doesn't need to see 1 million pictures of an elephant, right? It needs to see one picture of an elephant. And this is a little bit, I think we're coming closer to these sort of more intuitive ways of working for the models. Yeah, also these models are getting big. So for example, OpenAI CLIP we might also end up in the same state where, as for GPT, where there's just one model like that, it's the best, and everyone uses it through, an API. And so you just become sort of a prompt engineer maybe, and you are not the person to train the model anymore. Google does it for you. Now, for the last, let's say, 5 minutes, I want to talk about deep learning for time series. So time series are also very important, and I think they have been a little bit forgotten until recently by the deep learning community. So why do we care about that? In business, time series are everywhere. So it can be, for example, energy consumption, but also, anything related to logistics or also manufacturing or things like that, right? And if you look at the best techniques, historically, the best forecasting techniques, for a long time, we had things like ARIMA, exponential smoothing, models like that. They are working really well. They were quite simple. And they were winning, they were the best techniques. They were winning competitions until roughly 2018, where, what started to win was more combinations of these classical techniques together with some machine learning, right? And in 2020, this changed again. Now we have a deep learning model, which is called NBITS, which doesn't really care about the task. You don't need to really tune it. You just launch it, and if you have enough data, it turns very good forecasting models. So because there is such a sort of jungle of models out there for time series forecasting, we have at Unitate, we have built our own library for time series forecasting. It's called DARTS. I really invite you, if you are interested in time series, I invite you to check it out. It really attempts to make everything super simple, so you can just import whatever model, also deep learning models, and feed them using fit and predict future values using predict, like that. So this is another example. It makes it really simple also for deep learning. So we have NBITS, for example, implemented in DARTS, but we also have this model called temporal convolutional networks, and it just makes it really simple to train and to use. And before this talk, I just did a very quick experiment, actually. So I tried transfer learning using NBITS. So what I did is I created an NBITS model with DARTS. I fit it on a large data set of 48,000 monthly series that exists on the internet. And then I compare it to some exponential smoothing model, which is trained on air traffic time series. And then I ask both models to predict the future of this air traffic time series. So the NBITS model has never seen the air traffic time series. It's just been trained on many other time series, but not this one, right? And you can see that actually it does better than exponential smoothing. It's a little bit better. That's anecdotic, don't assume it will always be better, but it's super nice to see that we can do transfer learning for time series. I think I haven't really seen papers on that yet, but I think this sort of stuff also will come soon. So you can just have a model trained once and then ask it to predict the future of any other series, right? And because the model has seen, it's a bit like us humans, right? The model gets used to see these sort of seasonalities, there is an upward trend, and so on and so forth. So it's just good at interpolating series, right? All right, so yeah, I have to skip over this one quickly and go to the main conclusion. So transformer and attentions, they are eating this domain of deep learning architectures. I think they are coming everywhere. Models are really becoming huge. This is good. It allows things like zero one-shot learning, but it's also opening questions about, who controls these models. They can do cool things. So we can try to tackle combinatorial optimization using combinatorial problems using neural networks. We can do data-driven optimization or model-driven optimization using generative models. And we see more and more models that are sort of trained in self-supervised, semi-supervised ways, and that can work with just a few labels, which is also really nice. Combining modalities like image and text looks really, really promising. I think it will give a big boost to all of the models. And finally, transfer learning is also coming to time series, and deep learning in general is coming to time series. There we are. So thanks for the attention. I'm sorry because I know it was a lot of content, but I'm personally quite excited about this stuff. So I hope you liked it.